students. I'm very glad to welcome you all in this series of GATE Aerospace preparation classes. And I hope you all will get sufficient help from our efforts in achieving good rank in GATE 2021. Before I introduce our respected overseas speaker, a quick introduction and description about how our preparation module will go on in these days. So just like today, we will have conduct classes of 40 plus classes with different speakers with a gap of 2 to 3 days in between, and all the specific topic will be separated speaker wise, and you can find the topic wise detailed schedule from our course page in our website, and the lecturer detail also will be provided in the course page. The link is given in the description. You can follow the link, and these classes will be separated in 2 sessions. First session will be theoretical explanation. Just today we are going to have a theoretical explanation, and the second session will be solving previous year question papers and questions of the specific topic which we are going to have in the meeting. And you will get notes in PDF and PowerPoint presentation of our speakers, and the important notification will be sent to you in your mailbox. So don't worry, and let's get started. Today we are going to start this series with the aerodynamics subject, and we have our speaker Godwin and from Tech Aviation College, Uganda, Africa. So please, sir, our students want to know a little bit introduction about you, and then we'll start the lecture.
Thank you so much, coordinator. My name is Captain Godwin Anthony Ntia. I am the chief instructor of Space Tech Aviation College, Kampala, Uganda. I am very much delighted to be in this team 2020, and I want to thank the coordinator of this program. You are welcome to GATE Aerospace Preparation course by Team 2020. I will be taking you on the course Basic of Fluid Mechanics and Potential Flow. My name is Captain Godwin Anthony Ntia. You are welcome once again. We want to look at this theory part of the course Basic of Fluid Mechanics and Potential Flow. In the next section, we are going to be having equations and calculations. So I want us to have that at the back of our mind, that the basic is the mastery of the professionals. If you are able to master the basic, or you are able to know the theoretical part of the basics, you will be able to apply the calculations when you find them need be. So we want to go into the objectives of the course. Let us see the objectives of this course. Objective number 1 is to have the foundation or the fundamental knowledge or the basic knowledge of fluid mechanics. That is number 1 objective. Number 2 objective is that to understand the property and behaviors under various conditions of internal and external flows. That is objective number 2. Objective number 3 is to develop steady mechanical energy balance equations for fluid flow systems, estimate pressure drop in fluid flow systems, and to be able to determine performance characteristics of fluid machinery, e.g., hydrostatic law, principle of buoyancy, and stability of a floating body, and application of mass, momentum, and energy in fluid flow. Those are the objectives of this course. and there are more objectives that you can derive from this course. Let's look at the learning outcome. What is going to be the learning outcome after you might have studied this course? Number one learning outcome is that the student will be able to understand stress-strain relationship in fluids, classify their behavior, and also establish force balance in static systems. Further, they would develop dimensionless groups that help in scale up and scale down of fluid flow systems. That is learning outcome number one. The learning outcome number two is that students will be able to apply Bernoulli's principle and compute pressure drop-in flow systems of different configurations. You will be able to compute and understand the application of Bernoulli's principle. Then, number three, students will compute power requirements in fixed bed system and determine minimum fluidization velocity in fluidized bed. Then also students should be able to describe function of flow metering devices and apply Bernoulli's equation to determine the performance of flow metering devices. Then the last but not the least is that students should be able to understand and analyze the performance aspect of fluid machinery, specifically for centrifugal pump and reciprocating pumps. Those are learning outcome and etc. which you can derive from this course. So we want to look at the symbols. What are the calculation symbols that you might be finding in this theory class of basic fluid mechanics and potential flow? You are going to see most of these calculation symbols, the plus, minus, multiplications, divisions, the greater than, less than, is equal to, is not equal to, is similar to, is congruent to, infinity, is greater than. These are things you are going to see. Empty set, theta, implies, is equivalent to integral intersections of two sets. You are going to see this pi, you are going to see all these equations. So have this at the back of your mind, that the equations or these calculation symbols are necessary. But we might not be going into calculations in this theory. We might not be going into details of equations, but in the next section classes, we are going to be going into the details of the equations and calculations. Thank you very much. Now we want to look into definition. Let us look at the definitions of fluid. That is where we want to pass. We want to start from. The topic says basic fluid mechanics. What are the basic, the foundations? That is the fundamentals. That is what we want to look into. The fundamental fluid mechanics. How does it revolve? That is what we want to look into. Definition number one. Definition number one says a fluid is a substance that performs or that deforms continuously in the face of tangential or shear stress, irrespective of the magnitude of shear stress. This continuous deformation under the application of shear stress constitutes a flow. The deformation. A fluid is a substance that deformed continuously. It is a substance and it can deform continuously. That means it has a liquidation aspect of it. It can change its form. It can deform to any phase of tangential or shear stress that it has been applied to. That is what a fluid is. Then number two is, in this connection, fluid can be defined as the state of matter that cannot sustain any shear stress. We are going to see under this theory part of the study how fluids are being deformed, how shear stress takes place, and how viscosity takes place. We are going to look into that because this is a basic foundation that we need to understand on aerodynamics. Now, this is with the picture on your right hand side that shows the shear stress on a fluid body. Now, you understand that time makes the formation takes place. How? When you see that a substance is being applied of shear stress, then with time it changes, it deforms continuously as far as shear stress comes in. Now let's look at it. If a shear stress is applied at any location in a fluid, the element 011, which is on the image I showed to you, element 011, which is initial at rest, will move to what? 022, then to 033. Further, it moves to 044 and continues to move in a similar fashion. That is, when stress is applied to a fluid, it moves within time, which is within seconds, within minutes. It moves, and then you see that the shear stress has been applied to what? To the fluid, and it deformed. In other words, the tangential stress in a fluid body depends on velocity of deformation and vanish as this velocity approaches zero. A good example is Newton parallel plate experiment, where dependence of stress of shear force on the velocity of deformation was established. So, in tangential stress in a fluid body, depending on the velocity of deformations, as far as velocity is applied of the deformations and the velocity is approaching zero, there will be a vanish within the fluid. We are going to see this in more explanations as we go further. Now let us look at the distinction between solid and fluid, because someone might say, is fluid and solid not the same? No, they are not the same. Solid is different from fluid. What is in solid that you can't find in fluid, or what are the distinctions between the two that we have just mentioned? In solid, more compact structure. When something is solid, you will find more compact structure. But in fluid, less compact structure. Fluid takes the shape of the container that you drop it in. Now, attractive forces between the molecules are larger, therefore more closely packed. The attractive force between the molecules on inside solid, they do what? They are closely packed. But in fluid, attractive forces between the molecules are smaller, therefore more loosely packed. They are loose. That is, the attractive forces inside fluid are loose. That is why fluid and solid are not the same. Number three, solids can resist tangent stresses in static conditions. But in fluid cannot resist tangential stresses in static conditions. No, fluid cannot withstand that. Then number 4, whenever a solid is subjected to shear stress, two things happen. One, it undergoes a definite deformation or breaks. Two, it's proportional to shear stress upon some limiting conditions. There will be a proportion to shear stress because of its limiting conditions. But what happens in fluid? Whenever a fluid is subjected to shear stress, A, no fixed deformation. There will be no fixed deformation. Then B, continuous deformations take place until the shear stress is applied. You see, in solid, proportional stress, are you getting me now, is coming in because of limited conditions, because of some limited conditions. But in fluid, continuous deformation will take place until the shear stress is what is applied. Then the last but not the least, solid may regain partly or fully its original shape when the tangential stress is what is removed. But then in the aspect of fluid, a fluid can never regain its original shape. No, it can never. Once it has been distorted by the shear stress. So the different or the distinctions between the solid and fluid is many that we can mention, but these are just few that we can bring up on this theory class. Now let's move further. We want to look at basic fluid mechanics and potential flow theory. Now, basic fluid mechanics, conservation law, which are what? Mass, momentum, integral, and differential form. That is on momentum. Then the next one is potential flow theory. We are going to look at the potential. Now, potential flow theory is different from the basic fluid mechanics, but they go hand in hand. Now, the potential flow theory, we are going to be having sources, sinks, doublets, line vortex, and their superposition, like the viscosity, Reynold number, and so on. Then let us look at basic fluid mechanics. Conservation law. Conservation law can also be called law of conservation. In physics, several principles that state that certain physical properties, that is measurable quantity, do not change in the course of time within an isolated physical system. I come again in that. Conservation law, which it can also be called law of conservation in physics. Several principles that state that the physical properties, that is a measurable quantity of something, do not change in the course of time within an isolated physical system. Now, what does it mean? In classic physics, law of this type govern energy. When you talk about energy, momentum, angular momentum, mass, and electric charge. In particular physics, other conservation laws apply to properties of subatomic particles that are invariant during interactions, and important functions of conservation laws is that they make it possible to predict the macroscopic behavior of a system without having to consider the microscopic details of the cause of a physical process or chemical reactions. Now, in this basic fluid mechanics, we are going to see some little things that happens within some bodies that we might not take note until when we are in a class like this before we begin to notice how the process is begun. So let us look at conservation of mass. Conservation of mass. Conservation of mass implies that matter can be neither created nor destroyed. Matter can neither be created nor destroyed. That is, processes that change the physical or chemical properties of substance into an isolated system, such as conversion of liquid to gas to a gas. That is what the process of changing the physical or chemical properties of a substance within within an isolated system. That means changing, or you convert from liquid to mass. Example, you can put a water in a plastic and then you put it in a freezer. You are making a conversion of the fluid body into a gas form, but it will come out in the form of what? In the form of solid. Now, system leave the total mass unchanged. Strictly speaking, mass is not a conserved quantity. However, except in nuclear reactions, the conversion of rest mass into other forms of mass energy is so small that, to a high degree of precision, rest mass may be thought of as conserved. You see that? So, what is this? Now you see solid in the diagram, you see solid, you see liquid, you see gas. Now in solid, 1, solid is rigid. 2, solid is in fixed shape. 3, solid has a fixed volume. But in liquid, liquid is not rigid. Liquid has no fixed shape. Liquid has no fixed what? It has a fixed volume, but has no fixed shape. But when it comes to gas, gas is not rigid. Gas, no fixed shape. Gas has no what? No fixed volume. Because it can be disappear into the thin air. But it has no what? No, it is not rigid. It is not what? It is has no fixed shape. And it has no what? No fixed volume. But liquid has a fixed volume, but has no fixed shape. But solid has what? Has fixed shape and also has a fixed volume. Let's go to the next slide. Now, conservation of momentum. We have looked at conservation of mass. We want to look at conservation of momentum. General law of physics, according to which the quantity called momentum that characterizes motion never change in an isolated collection of objects. That is, the total momentum of a system remains constant. Momentum is equal to the mass of an object multiplied by its velocity and is equivalent to the force required to bring the object to a stop in a unit length of time. In here you can bring out a formula, but then we are not going to the equation now because we are on the theory part of this course. For any array of several objects, the total momentum is the sum of the individual momenta. There is a peculiarity, however, in that momentum is a vector involving both the direction and magnitude of motion, so that the momenta of objects going in opposite directions can cancel to yield an overall sum of 0. Now you see, here comes the equation. P equals to mv, which is P equals to momentum and m is mass, then v is velocity. Now let's see. You see, momentum equals to what? Equals to P, which is P represent momentum, and M represents the mass, and then velocity is for V. So let's go into conservation law, integral and differential form. In most engineering applications, the physical system is governed by a set of conservation laws. For example, the governing equations in gas dynamics correspond to the conservation of mass, momentum, and energy. These conservation laws are often written in integral form for a fixed physical domain. Suppose we have a physical domain with the boundary of the domain, then the canonical conservation equation, assuming that the physical domain is fixed, is of the form in which we have seen the equations. All this will be discussed with the equations and calculation in the next sections that we shall be having. Where U is the what conservation state, F is the flux of the conservation the conserved state, then in N is the upward pointing unit normal on the boundary of the domain, and S is a source term. So where U is what? U is the conserved state, F is the flux of the conserved state, then N is outward pointing unit normal on the boundary of the what of the domain, and S is the source term. Then we move to the this conservation law can be written as a partial differential equations by applying the divergent theorem, which state that. What is the theorem stating? Now you see equations which we shall be in the next section we shall be dealing with these equations bit by bit, and we understand where and how it is being derived from. So since these last equations must be valid for any arbitrary domain, this means that the integrand must be zero everywhere or equivalent. By next sections of this particular course, you are going to be having more of calculations and how the formation of equations comes about. So the above equations is the conservation law written as a partial differential equation. So that is what we shall be dealing with when we come in for the next sections, which is going to be practically on equations and calculations. Now let us look at potential flow. We want to look at potential flow. When a flow is both frictionless and irrotational, pleasant things happen. This was made by what? By F.M. White. He was a fluid mechanics first grade education. So he was the one who said this particular quote, which says when a flow is both frictionless and irrotational, pleasant things happen. So let's see. We can treat external flows around bodies as implicit, that is frictionless. When you hear that word implicit, means frictionless, and irrotational, which means the fluid particles are not rotating. So when you hear that word frictionless, you know it means implicit. And when you hear irrotational, you understand or have at the back of your mind that it means the fluid particles are not rotating. This is because the viscous effects are limited to a thin layer next to what? Next to the body, called the boundary layer. We have the boundary layer. The boundary layers are the, let me take example of explanation. Now when you put your two hands together and you want to rub it, when you are rubbing your two hands, Remember, your palm has what? Has a layer, and the layer of the two hands comes in together, which is called the boundary of the two hands. Except you rub the two together, that is when the friction or shear stress is applied, and then you get what you are able to sense in your hands while rubbing the two together in straight form. Now, the both hands have what we call boundaries, which is the layers of your palm. That is what it means here, that the boundary of the layers. In the next class to come, you will learn how to solve for the implicit flow and then correct within the boundary layer by considering viscosity. For now, let us learn the theoretical part of this course. Now, we can define a potential function as a continuous function that satisfies the basic laws of fluid mechanics, which we talked about: conservation of mass and momentum, assuming incompressible, implicit, and irrational flow. That we see. So, potential function and stream functions. Now you see the sign for potential functions and the sign for what? For stream functions. Can be defined for various simple flows. These potential functions can also be superimposed with other potential functions to create more complex flow. We are going to see that more complex flows. Now, potential or irrational flows theory. What are potential flow theory? Or what are irrational? Because you can call it irrotational or you call it potential flow. So, what is potential or irrotational flow? It's a cornerstone of fluid dynamics for two reasons. Historically, its importance grew from the development made possible by the theory of harmonic functions and the many fluids problems thus made accessible within the theory. So, but a second more important point is that potential flow is actually realized in nature, or at least approximated in many situations of practical importance. Water waves provide an example of potential flow because they are naturally realized in nature. So water waves provide an example. Here, a fluid initially at rest is set in motion by what? By passage of waves. When you go to the river, you go to the boundary of water, you see some waves. Are you getting me now? Now, what happens? The fluid is initially at rest. The water it has rest is on the rest body. Now, the motion by the passage of waves on top of the water. Now, Kelvin theory ensures that the resulting flow will be irrational whenever the viscous stresses are negligible. We shall see in a later chapter that viscous stresses cannot in general be neglected near rigid boundaries. But often potential flow theory applies away from boundaries, as in effect on distant point of the rapid movement of a body through a fluid. Let us see line source flow. Line source flow. Source flow. This is a radically symmetrical flow filed directly towards from a common point called a source flow. The central common point is the line source Line source described as a line source in a line from which fluid appears and flows away on planes perpendicular to the line. As the fluid flows outward, the area of flow increases. As the fluid flow outward, the area of flow increases. As a result, to satisfy continuity equation, the velocity decreases and the streamlines spread out the velocity at all points at a given distance from the source is the same. The velocity at all points at a given distance from the sources are the same. Now you can see the equations, then you see the uniform flow, then we have the doublet, we have the vortex, then we have the uniform flow, we have the doublet, then you can see the stagnant point. But now we are not going to go into the equations and calculation of it because we are still dealing on the theory flow of it. We need to understand the definitions and how it comes about before we go into deriving equations on them. Let us see line source or sink continuation. Sink flow. This is the opposite of source flow. That is very simple to understand. Sink flow is an opposite of source flow. The streamlines are radial, that is radial, directed inward to the line source. In order to satisfy the continuity equation, the streamline get bunched closer and velocity increases as we get closer to the source. As with source flow, the velocity at all points equidistant from the sink is equal. Now remember, when the source is moving, it moves and get larger and larger. The distance are still the same. The distance are still the same. So the velocity of the flow around the sink can be given by, you see velocity and then you see the equations. Now the flow around a line is irrational. Now we are not going to go into the details of calculations and how we derive, but in the next sections we are going to be doing that. Then we have doublet. A doublet can be thought of as a combination of a source and a sink of equal strength. Keep in mind what equal strength kept at an infinitesimally small distance apart. They are just infinitesimally small distance apart from each other. That is what you see droplet is. Droplet is the combination of the source and the sink of equal strength kept at infinitesimally small distance. Thus, the streamline can be seen to start and end at the same point. They are ending at the same point. As they are spreading out, they are ending at the same point. So that is droplet. Now let us look at line vector and their superpositions. Now by the next classes or the next sections that we are going to be having, we are going to be seeing calculations in all this that we have discussed so far. Now line vortex and their superposition. A vortex line is a line everywhere tangent to. A vortex line is a line whose tangent is everywhere parallel to the local vorticity vector. The vertex line drawn through each point of a closed curve constitutes the surface of a vertex tube. Finally, a vertex filament is a what? Is a vertex tube whose cross section is of what? Of infinitesimal dimension. Who is what? Infinitesimal dimension. Now, in this diagram, you can see the vertex filament of strength being drawn. Now, we are going to see more of examples. Then you see the leading edge. Now, this is what? This is a camber. This is a camber of an aircraft, which is the wing of an aircraft. We are always, everybody knows the physics. When you are in the aviation industry or the industry that we are into flying, you definitely know. I might not want to go down to start describing the wings of an aircraft to you and the controls which is on it. But then with Vortex, which we want to discuss, and then with many things which is based on aerodynamics that we're going to discuss, it's going to be a very minimal but basic. Now, this is the picture or the shape of a camber. We have the leading edge, we have the bound vertex, then we have the what? We have the control point, and then we have the trailing edge. The trailing edge of a wing is where you always have what? You always have the flaps. Then on the camber you have the spoilers. Then at the what? At the leading edge you have the slat. Then at the tiny control point length you have the ailerons. But now that is not what we are going to. We are dealing with our vertex, line of vertex, and then you can see the picture of a camber. You see the filament and the what? And the bound vertex. Now this is the what? The camber line. This is a camber line, and this is a camber line here that you can see with the line of what? Of vertex. Now we will go into the next. Now let us look at viscosity. Now we would see viscosity and the shear stress that has been applied in this, how it comes about. Now the viscosity of a fluid is a what? Is the measure of its resistance to deformation at a given rate. The significance of the parameter appearing in previous expression for the stress tensor can be seen from the form taken by the relation in the special case of simple shearing motion, with as the only non-zero velocity derivative, all of the components of zero part from the what? From the shear stresses. Now we are going to see on this video viscosity, and then you see stress, you see a shear stress that is on it. I'm going to play this video. You might not hear the audio part of the video, but the picture part of it is what I really want you to take into practice. So I'm going to play this video before I continue in the next class. So let us look at the video. Viscosity. That is a red fluid. And this is a green color. And then we want to put blue corn syrup. So let's see what shear stress does, and let's see how it's going to be. Now it's going to be rotated slowly into 5 times. That is 2. And that is 3. This 3. 4. And this is 5. So we are going to return back on the experiment we want to see. That is 1. That is 2. And that is 3. And this is 4. And then we return back to this. Now you see this is viscosity that has just taken place. Now let's go to the next slide and then discuss. Thus, viscosity is this constant of the proportionality between the rate of shear and the tangential force per unit area when parallel plane layers of fluid slide over one another. Did you see that on that video? This constant of proportionality is generally referred to as viscosity. It is a matter of what? Of experience that the force acting between layers of fluid undergoing relative sliding motion always tend to oppose the motion, which implies that U equal is what? Is greater than what? Than 0. But now we are not going to go into this viscosity equation now. We are going to be doing that in the next what? In the next sections. Now let us look at Reynold numbers. We want to look at Reynolds number. Now the Reynold number help predict flow patterns in different fluid flow situations. Reynolds number helps us to do what? To predict flow patterns in different fluid flow situations. The Reynolds number is the ratio of initial forces to viscous forces within a fluid which is subjected to relative internal movement due to different fluid velocities. A region where these forces can change behavior is known as a boundary layer. That is the region at which, now we just saw a video of viscosity. You see that the layers at which, as the fluid was being turned, it starts getting sprayed with the layer because of what? Because of shear stress. But as it was returned back, you see that every layer started beginning to do what? To return back to its position. So such as the boundary surface in the interior of a pipe. So a similar effect is created by introduction of a stream of high velocity fluid into a lower velocity fluid, such as the hot gases emitted from a flame in air. This relative movement generates fluid frictions, which is a factor in developing turbulent flow. We have different kinds of flow, but now we are dealing on this. So let's see the Reynold number and how it helps to predict patterns. Counteracting this effect is in viscosity of the fluid. which tend to inhibit turbulence. The Reynolds number quantifies the relative importance of these two types of forces for what? For given flow conditions, and is a guide to do what? To when turbulent flow will occur in a particular situation. So how does this work? This ability to predict the onset of turbulence flow is an important design tools for equipment such as piping system or aircraft wing. But the Reynold number is also used in scaling of fluid dynamics problems and is used to determine dynamic similitude between two different cases of fluid flow, such as between a model aircraft and its full-size version. Such scaling is not linear, and the application of Reynold number to both situations allows scaling factors to be what? To be developed. So what do we have? With respect to laminar and turbulent flow regimes, one, laminar flow occurs at low Reynold numbers, where viscous forces are what? Are dominant, and is characterized by smooth, constant fluid motion. Turbulent flow occurs at high Reynold numbers and is dominated by initial forces, which tend to do what? To produce chaotic eddies, vortex or vortex, and other flow instability. That is what turbulent flow does. But laminar flows occur at Reynold numbers where viscous, which is low Reynold numbers, which viscous forces are dominant, and is characterized as smooth, constant flow motion. That is a smooth. Now, when aircraft is flying and then is not having a smooth flow, that means the fluid in the air are not what? Are dense. At least they are in dense situation. Now let's see Reynold number. Reynold number is defined as you can see on the equations. As you can see on the equations. As you can see on the equations. Then P is the density of the fluid. Density of the fluid, SI unit. Then U is the flow, speed flow, the speed flow that you can see on the equations. Then L is a characteristic linear dimension. Then U is the dynamic viscosity of the fluid. V is the kinematic viscosity of the fluid. Then to give a definition that generally include the fluid properties of density and viscosity, fluid, a velocity, and a characteristic length or characteristics dimensions. Now I'm going to come back to give this so that you understand this, that we have the equations there. Re, which is Reynold number, equals to what? Density of fluid, velocity of fluid, and diameter of pipe. Then over diameter viscosity of fluid. To give a definition that generally includes the fluid properties of density and viscosity, plus a velocity and a characteristics length or characteristics dimension, which is L in the above equation. We say Reynold number can be defined for several different situations where a fluid is in relative motion to a surface. Is that okay? So let's see airfoil and wings. We want to see airfoil and wings. Okay, an airfoil in American English, it is called airfoil, but in British English, it is called aerofoil. Is the cross-section shape of a wing, blade, or a propeller, rotor or turbine, or sail of an aircraft. So an airfoil is what is the cross-sectional shape of a wing. That is the cross-sectional of a wing on an airplane. So an airfoil shape body moving through a fluid produces an aerodynamic force. The component of this force perpendicular to the direction of motion is called lift. The movement, I repeat, the movement through the fluid, which is in perpendicular, is called lift. The component parallel to the lift of motion is called what? Drag. Now we have, when you hear about the four forces, aerodynamics, the four forces of aerodynamics, which is lift, drag, weight, which is gravity, and what we have, thrust. Then so the component parallel to the direction of motion is called what? Drag. Subsonic flight aerofoil have a characteristic shape with a rounded leading edge, following by a shaped trailing edge, often with a symmetric curvature of upper and lower surfaces. Foils of similar functions designed with water as the working fluid are called hydrofoils. So hydrofoil is what is the functions of design, that is those that are working on water. That is why you see that word hydro. Hydro comes from the word hydrogen. Are you getting me? Water. So let's see, this is a cross section. You have on here the shape of an aerofoil. You have the leading edge, you have the leading edge and the radius. You have the location of the maximum thickness. Then you have the maximum thickness, which you can see the length, and then you have the chord line in red. Then you have the maximum camber. Then you have the main camber at the rear, and then you have the trailing edge. That is the longitude of the chord, and then you can see the locations of the maximum camber. This is a cross-sectional shape of what? Of a wing, which is called camber and airfoil. Okay, let's see. Now, the lift on an airfoil is primarily the result of its angle of attack. When oriented at a suitable angle, the airfoil deflects the oncoming air by making use of what? Flaps. Now, deflect the oncoming air for fixed wing aircraft, a downward force is generated, resulting in a force on the airfoil in the direction opposite to the word deflection. This force is known as what? This force is known as aerodynamic force, and can be resolved into two components, which is one lift, two drag. Most foiled shapes require a positive angle of attack to generate lift, but cambered airfoil can generate lift at zero angle of attack. That is when flying an aircraft. So when taking off, there are different mechanics that need to be applied. In the case of what? In the case of non-cambered airfoil. Okay, so this turning of the air in the vicinity of the airfoil creates curved streamline, resulting in the lower pressure on one side and higher pressure on the other side. So what happens? This pressure difference is accompanied by a velocity difference via Bernoulli's principle. So the resulting flow field about the airfoil has a higher average velocity on the what? On the upper surface than on the lower surface. In some situations, that is implicit potential flow. Remember what implicit potential flow is. The lift force can be related directly to the what? To the average top and bottom velocity difference without computing the pressure by using the what? The concept of circulation and the Kota-Djokovic theorem. Kota-Djokovic theorem. So these are what we want to also look into, and then we have viewed the basis of aerofoil on the wing and the camber, which is on aerodynamics. Now remember the two forces that are very paramount, which is the aerodynamic forces. We have four, but there are those that are very important to look into. Not about the gravity or the weight of the aircraft, but about the lift and the drag. How does it thrust? Without thrust, we can't create drag. And then without lift, we can't overcome what? We can't overcome gravity, which is the weight. But then let us look at the various terms related to airfoil. So let's look at it. Now the various terms related to airfoils are defined below. The suction surface, aka which is the upper surface, is generally associated with higher velocity and lower static pressure. Then we have the what? We have the pressure surface, aka lower surface, as a comparatively higher static pressure than the suction surface. The pressure gradient between these two surfaces contribute to the lift force generated for a what? For a given airfoil. Generated for what? A given airfoil. Now the geometry of the airfoil is described with a what? With a variety of terms. So that is what we want to do. What we want to look into. Now, one, the leading edge. The leading edge is the point at the front of the airfoil that has maximum curvature, which is minimum radius. Then we have the what? The trailing edge. The trailing edge is defined similarly as the point of maximum curvature at the rear of the what? At the rear of the airfoil. The cut line, we have the cut line, which you see the dot from the leading edge to the trailing edge, is the straight line connecting leading and the trailing edge. The cut length, or simply cut, which is used, challenge C, is used as what? As a symbol for cut. Now is the length of the cut line, that is the reference dimension of the airfoil sections. So let us see the shape of the airfoil is defined using the following geometry parameters. The main camber line, or the main line, is the locus of what? Of the point midway between the super and the lower surfaces. Its shape depends on the thickness distributed along the chord. So that is a geometry parameters about the airfoil. Then the thickness of an airfoil varies along the chord. It may be measured in either or two ways. One, which is what? The thickness, measured perpendicular to the camber line. This is sometimes described as the American convention. The American convention. So thickness measured perpendicular to the chord line. This is sometimes described as the what, as the British convention. Note some important parameters to describe an airfoil shapes are its camber and its thickness. Those are the parameters to use in describing an airfoil shape. Okay, so now let's see a wing. We want to look at the wing. That is what we want to look into. The wings. A wing is a type of fin that produces what? Lift. While moving through air or some other fluid. As such, wings have streamlined cross sections that are subject to aerodynamic forces and act as airfoil. So, wings have streamlined cross sections that are subjected to aerodynamics forces and act as airfoil. A wing aerodynamic efficiency is expressed as its lift to drag ratios. Remember, in the former slide, we talked about the two forces that are paramount, which is the lift and also the drag. Now, the lift a wing generates at a given speed, an angle of attack can be 1 to 2 orders of magnitude greater than the total drag on the wing. So, a high lift to drag ratio requires a significantly smaller thrust. Thrust is the moving forward. Thrust to propel the wings from the air at sufficient lift. So thrust does what? Thrust moved the aircraft forward. Is that okay? So then let's also see design features. What are the design features that we need to note? Aircraft wings may feature some of the following. 1. A rounded leading edge cross sections. That is one of the features of design that you might see. Number 2, a sharp trailing edge cross sections that you are going to see on the aircraft wings. Then you are going to also see leading edge devices such as slats, which I have mentioned before, slots or extensions. Now you find out that in the passenger aircraft, you find out that at the wing you would find these controls: the slat, the spoilers, you find the flaps, you find ailerons. Now, trailing edge device such as flaps or flap runs, combination of flaps and ailerons together. That is why you see that word called flaperons. So, winglets to keep wingtip vortex from increasing drag and decreasing lift. You will see winglet. That's what we call winglet at the tip of at the last tip of the wing of an aircraft. Then you will have the hydral or a positive wing angles to the horizontal. Increases spiral stability around the roll axis. Whereas an hydral or a negative wing angle to horizontal decreases spiral stability. That is another topic that by the time we go into it, we shall see or know many more about wings. But then let's look at this. Okay, aircraft wings may have various devices such as flaps or slats, spoilers, ailerons that the pilot uses to modify the shape and surface area of the wing to change its operating characteristics in flight. Now, besides fixed wing aircraft, Applications for wing shapes include: 1. Hang gliders, which use wings ranging from fully flexible, like the paragliders, the gliding parachute, flexible frame frame cell wings, too rigid. Then we have the kite, which use a variety of lifting surfaces. Then we have flying model airplane, right? Then we also have the helicopter. Now in the helicopter uses a rotating wing with a variable pitch angles to do what? To provide directional forces. Then also propellers, whose blades generate lift for propulsions. Then the NASA Space Shuttle, which uses its wings only to do what? To glide during its descending to a runway. This type of aircraft are called space planes and etc. Now, if you look at your right hand side of these presentations, you will see types of wings and their names. You see the elliptical wings, you see the rectangular wings, you see the moderate taper wings, then you have the higher taper wings, then you have the pointed tip wing, and then you have the sweep back wing. Many times the passenger aircraft uses the sweep back wings. Now that is not what we want to go into definitely. I will not talk about the passenger aircraft wings and all that, but then we have been able to see the characteristics of a general airfoil. All the wings that are mentioned here has these characteristics that we have discussed so far. I want to say a very big thank you to the team for putting up these lectures to students, and I want to also thank you very much for having time to sit for this lecture and to listen to me and also to partake in this lecture. Have a blessed day and thank you very much. So I say good day to you all. Thank you very much and have a lovely day.